Thank you. Good morning. So this is a talk about spectral geometry. And spectral geometry, of course, means relating the geometry of a space. In today's talk, it's going to be a graph with weights on the edges, but the techniques go over to quite general spaces, to something like the spectra, the eigenvalues, eigenvectors of something like the Laplacian. And it goes both ways. In statistical applications, spectral clustering, which is one of the themes of this week, people try to look at, well, the eigenvectors and try to learn something about the geometry of the space. And I'm going to be using the geometry of the space to understand something about the spectrum, but it really does go both ways. The new thing today, the reason I'm giving this talk, is that we have a lot of insight and experience with geometric methods, and there are some different operators, not just the Laplacian, where the methods still are effective, can be effective, and there's a lot to do in trying to push that forward. So let me begin by reminding you what kind of one classical use of spectra is, what I call the geometric theory of Markov chains. So if X is a finite set, and pi of X is a probability distribution, and if you have a Markov chain, so the transition matrix of a Markov chain, and I'm going to suppose it's reversible. So you could think of a graph in which the vertices are x, and there's an edge from x to y if kxy is positive, and then you put this weight on the edges. And then I'm going to be talking about doing the random walk on the graph. So if you're at a vertex, pick one of your nearest neighbors with probability proportional to its weight and go there. I think about it this way, but it's the same process. Because of this symmetry, because of this reversibility, there's a basis of eigenfunctions. So there exists phi I eigenfunctions such that k phi I is beta I phi I of x. Here I use the notation kf at x. It's just column vectors. It's the sum of k of xy, f of y. So there is an orthonormal basis of eigenfunctions and eigenvalues, real spectrum, and then you can get your hands on the rates of convergence if k squared of xy is the sum of k of xy, xz, k of zy. So if you divine, it's the product of the matrix, square of the matrix, or anyway, everybody knows, this is a sum in Z, then you can get your hands on the distance to stationarity, and I'll use this total variation distance, which is, well, 1/2 the sum of KL of xy minus pi of y. Here's sum over y, and it should have an x in it, because keep track of where you started. So one would like to answer the question, given epsilon bigger than 0, how large should L be so that this is small? And you can get your hands on that using this bound. I want to bound this thing, and so I can bound it square. Take square roots later. This is less than or equal to the sum over I equals 1 to the space of the the zeroth eigenfunction is 1 of beta I, the eigenvalue to the 2th power, times phi I of x squared. So this is a basic, this is the Cauchy-Schwarz inequality. This is the basic geometric bound, which says that if you know about the eigenvalues, you could know about the rates of convergence. Sometimes we use a crude upper bound on this. It's less than or equal to the spectral, the second eigenvalue divided by pi of x. And so if we can bound the second eigenvalue, and if we know something about the stationary distribution, we can know something about convergence. So that's all now classical. And but now the work starts, given some actual Markov chain, and then you have to get your hands on this and try to get your hands on these and then do the analysis, and that's a job. I mean, that's okay. So the first new problem was new to me, is absorbing Markov chains. And quasi-stationarity. And so just as a picture, picture a graph. Here's some graph, and there's some bad part on the boundary. And maybe here it's just, here if you hit, you go back just the usual way. But here if you hit, you stop. And so you stop eventually if the graph is connected. It's an absorbing Markov chain. And there's lots of that around. I wasn't so aware of it, and I ran into it in some applied problems. And then it's natural to ask, well, what can you say along these lines about an absorbing Markov chain? And examples are coming in a second. Okay. So first let me introduce some notation. If I write down here, can people see it? Is it still okay? Yes. Okay, good. So let me introduce some notation. I'm going to lump, for now, I'm going to lump all of the absorbing states into one state. You won't lose too much, which I'm going to call infinity. That's okay. And then I've got a matrix, which here's infinity, and so if you hit infinity, you stay there. Okay, but of course you can get to infinity, so there's some a1, maybe up to an. This is my matrix K, Kij now, and here is some n-1 by, here's some big block, what's left of K, just not at infinity. And so, this is the chance of going from J to infinity, this entry. And so what you observe is that this Q is a positive matrix, non-negative matrix, and therefore, by Perron-Frobenius, there exists phi of x and psi of x and beta, all bigger than 0. These are functions. I'm going to assume Q is connected, that you can get from any place to any place else, such that this is such that phi Q is equal to beta phi, and Q psi is equal to beta psi. So these are the Perron eigenvectors of this matrix Q, and they exist. And let me tell you what they mean, so that will be important. Okay, so there are left and right eigenvectors and a positive eigenvalue beta. So what do they mean? Well, look at Q to the nth power, and look at the xy entry. First of all, what is that? It's the sum over all paths going from x to y in L steps, which don't ever hit infinity, right? So got a very simple interpretation. And this converges, of course, to the left, to phi of y, phi of y. And let me normalize it by, so that it becomes a probability, qx, and that converges to phi bar, where here I use the notation q bar of x to be the sum in y of q L, L of xy. So this is just the chance of not being absorbed all after L steps, and phi bar is the normalizing constant here. Phi bar is just the sum in x and phi of x. So this is just elementary, and what this says is that if you run, what this says, I'll write it down various ways. What this says is if you run the chain a long time and you haven't died, you can ask, where are you likely to be? That's what this means. This is called the quasi-stationary distribution. Okay, so so if in probabilistic language, if t is the first time you hit infinity, is equal to the first time you hit infinity, this says that the probability that the Markov chain started at x is equal to y at time t, given that capital T is bigger than t, converges to this phi of y over phi bar as t goes to infinity. And so that's, I'll give examples in a second, but that's what the left eigenvector means. What does beta mean? So what does beta mean? Beta, it's the absorption time, but there's a nice interpretation of it directly. You can look at this, what's the probability given that you started at this quasi-stationary distribution, just to make something precise, given that you started at phi over phi bar. Okay, so you pick your starting state from this measure. You can also do it starting from a point. What's the probability, given that you started from there, that capital T is bigger than little t? That's exactly equal to, no asymptotics, beta to the little t. So that tells you what beta means in a sort of direct probabilistic way. And what does the right eigenvector mean? I'll tell you that too. And this is just all, Frobenius and thinking in a kind of an applied way. What does the right eigenvector mean? Well, if you okay, this has a fancy name, but I won't. If you look at this matrix, qxy, and then multiply it by psi of y, and then divide it by psi of x, and times beta. Okay, so that's a new matrix. This matrix is stochastic. If you sum this in y, okay, because this is a right eigenvector, you get beta times psi of x, and you get 1. Right? So this is a stochastic matrix. And it has a name. It's called the Doob transform. And what it means is it's the law of the Markov chain, given that it's never absorbed. And so, maybe somebody tells you, or I can condition, it makes sense to say, well, I'm running this chain and it never got absorbed. How does it go? And this is again a Markov chain, and it's very closely connected to quasi-stationary distributions. And it has as a stationary distribution, again, these are very easy facts, phi of x times psi of x, then normalized times phi psi bar. And you can just see that if you multiply this on the left by phi psi and then sum it, you know, this cancels and you have a left eigenvector and it's okay. You know, it's just trivial what I'm saying. Everything I'm saying is easy. So,
is there some additional assumption you're making on Q besides
I'm assuming that
connected?
Not really. I mean, you mean something about parity or something like that? I mean,
No, like imagine that the Markov chain just a directed path that ends at infinity. Then with probability 1, you are absorbed in finite time.
no. Yes, but I'm conditioning. First of all, forget anything. This is a stochastic matrix. This matrix.
No, I was looking at the previous. The equation on the top of the rightmost board.
This.
So this says that you have non-zero probability of.
I think this is true just under connectivity, but I'm starting from the stationary distribution. This is again, it's an algebraic verification. I don't think that is, of course, with probability 1. You know, this beta is less than 1. So with probability.
Well, imagine you have a part of length 3 that ends at infinity.
Yeah.
The directed part of length 3 that ends at infinity. Then the probability that capital T is more than 4 is 0.
But I'm assuming. Well, I'm in the reversible case. I'm in the reversible case.
But how can an absorbing Markov chain be reversible?
Oh, it's reversible on the. Sorry, it's reversible on the non-absorbing states.
I see. So Q is reversible.
Right.
Okay.
Yes, for this interpretation, Q is reversible. Right. I've said K is, well, okay, I didn't say that. Good. I'm going to assume it, you don't need that, but, okay, I haven't gotten even started, but thank you for listening. So these are, I try to tell you what the eigenvalues and the eigenfunctions mean. Now, when you see this kind of thing, if you're me, it's natural to ask for quantitative theory. So,
by thinking of just the heat equation and a boundary condition?
You could, if you like that language.
No, but is it identical or not? So
If you have a domain in Rn, I mean, it's not identical. These are matrices, young man. So if you have a domain in Rn, and if you have Brownian motion in the domain, then
no, but wires. So my domain.
I don't know about wires, Gary. I don't know about wires, so if you have a domain in Rn, and if you have Brownian motion in the domain, then this is the Dirichlet eigenfunction, if you vanish on all of the boundary, and that has the interpretation as, if you've been running Brownian motion for a long time, and it hasn't been absorbed, where's it likely to be? And that's what phi is.
And that would be the first set of eigenvectors you found, right?
That's the first left eigenvector. There's a left eigenvector and a right eigenvector. And good, thank you. Okay, so it's natural to try to think about a quantitative version of these things. And here it comes. So
this conditional distribution, given that you didn't absorb for time t, does it converge as t tends to?
That's just what I'm about to say. Thank you. Hi and good morning. Friends in the audience. So a natural question, if you're many of the people in this audience, is how large should K be, so that I'll write it this way, that the probability starting at x, that xk, is contained in dot. I mean, the probability distribution, given that t is bigger than k, minus this phi over phi bar, the quasi-stationary distribution, say in total variation distance, is less than epsilon. That is, I know that as k goes to infinity, this probability distribution converges to this probability distribution, and you can ask about, how large, when do these asymptotics kick in? And and I thought, well, there's a giant literature on quasi-stationarity. I mean, books, hundreds and thousands of papers. That's a natural question, and it seems to have not ever been addressed, essentially. So everything I'm going to tell you now is from a technical report with Laurent Miklo, and it's on my homepage and on the archive. And it's rates of convergence to quasi-stationarity. And let's see what I'm going to tell you, because I had to make some choices. And first thing is an example. That's always good. And okay, so example. Just, what does a theorem look like? Suppose that I just have a path, as Luca was saying, and it's go this way, but you die when you hit that, and here's n. Okay, it's a path of length n, and I just am doing simple random walk, and so there's a quasi-stationarity, and one of the questions is what do quasi-stationary distributions look like? How can you get your hands on them? How can you understand them? Here, the quasi-stationary distribution phi of x, I'll call this 0, 1, up to n, is equal to, there's a normalizing constant, which we know, times cosine. Why should I make it up when I wrote it down? Can I read my own writing? 2n plus 1, 2n plus 1 minus 2x times pi. I'll draw a picture, which is really what's needed, over twice 2n minus 1. And so the picture is, here's 0, here's n. The picture is it's like this. So you've been wandering around for a long time. It doesn't matter, this is a limiting theorem. You've been wandering around for a long time. You die if you're at 0. If you hit 0, where are you likely to be? And the answer is you're kind of here. Okay, but this is exactly the answer. And as a theorem about rates of convergence, how long does it take until this is usefully close? Suppose you start here. Theorem if n is bigger than, there's a constant, which I actually also wrote down, s times 5 over 2 pi squared times n squared. Starting at n, then this distance is less than or equal to e to the minus s. And so, and there's a matching lower bound. Which?
On the left-hand side, instead of n,
This is n. T. This is k. Thank you. This is k. How many steps? You're right. Thank you. Right. So if you go a small multiple of n squared steps, these asymptotics are useful. If you go a small multiple of n squared less, the 10th n squared steps, this distance is very far from being small. And
sorry, does it depend upon where you start? Is it
this particular, it can really depend on where you start. This particular result doesn't depend on where you start, but it can depend on where you start. And here I'm depending. This particular result, it's also true even if you start one away, right? Because the actual statement that I'm making. So you now can see, so you could ask, take any problem that you think you know about, take the hypercube, take a tree, take anything. You die if you hit some vertices, and then do the random walk, say anything about the quasi-stationary distribution, say anything about the rate of convergence. That's a class of problems. Okay, now there's many, many natural problems. Take the permutations, take random transpositions. You die if you have a fixed point, I don't know, or something. I mean, there are many ways of making questions, and you'd have to look. So how are such theorems proved? Okay, so here's a thing that I found, well, disturbing or exciting, depending on how you want to phrase it. In the first setting, ergodic Markov chains, we have many, many techniques for bounding the spectrum and proving theorems of this sort. For ergodic chains, you know, we can use Poincaré, Cheeger, Nash-Sobolev inequalities, log Sobolev, coupling, stationary times, Harris recurrence techniques. Okay, there must be analogs of these techniques in the set of problems I just mentioned. I don't know them. I don't think anybody knows them. Okay, so that's a no. So let me tell you where we are, because we just got started building a theory, and I think there's plenty of things to do for anybody who's interested. This is a conference on spectral geometry, so I'm going to take a spectral geometric approach. So here's the spectral geometry approach. And I should say I'm not doing it in this talk, but the paper I wrote with Miklo has good pointers to what's the literature on quasi-stationarity. It's a healthy, big literature. It just doesn't. It's just not quantitative, but they do. There's a lot of interesting things that are done there. Okay, so spectral geometry. So let me assume that Q is reversible with respect to something. In this example, the Q matrix is symmetric. So say that there exists Q of x bigger than 0, such that Qxy is equal to Qy Qyx, and in our example, this Q, in that example, it's symmetric, but otherwise you want to allow that. So suppose that's the case. Our paper is written without that assumption, but let me assume it for now. And connected, this is connected. So now this is the undirected case, and you know what I mean by connected. And then there is there's a Dirichlet form. So let L2 of Q just be equal to the set of all functions for f from x from what to call it. Let me suppose that x is S union infinity. Okay, the non-absorbing states are called S, and f from S into C or R, say R, with the Q, with the norm of f. So Q squared is the sum of f of x, Q of x, x and S. And if it comes up, if I write it and you get nervous, f of infinity extend equals Q of infinity equals 0 if it comes up. Okay, so just.
We want to square on the f.
Careful audience. Good. Okay, so there's a Dirichlet form, and it took forever to get it right. So it seems trivial, but it took forever to get it right. Let E FF, this is the appropriate quadratic form, to be 1/2 the sum over x and y in x, allowing infinity of f of x minus f of y squared times qx times qxy. And so we think, well, wait a second. there are terms in here, you know, if one of them is infinity and one of them isn't, there are terms in here that involve. This is a careful choice. You can't do the more naive thing of just summing over S. Okay, so that's the Dirichlet form, and fact one is that if there exists an A bigger than 0, such that the L2 norm of F squared is less than or equal to A times EFF, so for every F, then beta is less than or equal to 1 minus 1 over A. Of course, that's the variational characterization, but if you look, it's annoyingly tricky. And anyway, that's a easy to believe fact, and it's also true. And so, okay, good. Of course, we knew that. And fact two is we can bound it by geometry. So let's say that. So fact two, let's choose paths for every x in S. Let gamma x be equal to, well, x naught, which is x, x1, x2, up to xl, which is equal to infinity. So make a path in your graph from x to infinity where the steps are possible, where q xi plus 1 is bigger than 0. So connect your point x to infinity, and if there's a lot of infinities, there might be, you're allowed to connect to any place, to any infinity. So make a path that connects you from a point to infinity. And the length of this path is L. And now there's a bound. You can take A, this is a fact, take A to be equal to the maximum over x contained in S, y contained in x, allowing infinity, of 1 over q of x, q of xy, times the sum over z, such that xy is contained in the path c of the length of the path times q of. So this is a geometric bound for people who know about geometric theory of Markov chains. These are the use of paths that Dan Strouk started, and Alistair Sinclair and Mark Jerram carried on with, and Dan Strouk and I carried on with. So this is the path argument, and so these kinds of, if you haven't seen them, it looks impossible. These kinds of quantities can be usefully bounded, and you get a bound on the second eigenvalue. Let me say one sentence about the argument, just so you see where this condition comes from, and then you'll say, oh, it's the old argument, and it is sort of the old argument. How does it work? You write, I need to bound this L2 norm, so I'm going to write f of x as, well, f of x minus f of x1 plus f of x1 minus f of x2 plus f of xl minus 1 minus f of xl. Okay, now that's 0. Right? That's 0. And so this collapses. And then just use Cauchy-Schwarz. Right? It's just the same now. So the square of this is less than or equal to the length of this path times the sum of squares, and blah, blah, blah. So
if that's square,
I haven't squared anything yet, but if I do, it's okay. Now use Cauchy-Schwarz.
I mean in A.
No.
Just about the line.
Where are you?
Yeah.
Where?
When A is equal to the max?
A is equal to max of blah 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 f squared.
No.
No?
No. This is Q.
Oh, that's cute. For all that.
Right. And in many cases that cancels, right? So let me just go through this example just so you can see what happens. Just so you see you can use this technique. So suppose I'm in this example. Okay, so I've got a point here. There's only one way to connect it to infinity. Just connect it to infinity, right? Just go that way. There's nothing else you could do, really. And what happens is, where's the edge with the worst traffic? It's this edge, right? Everything will cross over that edge. So that's the edge which maximizes this bound. And here, q of xy, because these q's cancel. This q of xy is a constant. It's 2. This actually should be a 2. Sorry about that, but it should be a 2. And so this is a constant. It's 2, the chance of going left to right. The length of a path, you know the length of a path. And so if you use this argument, you get in the example, when I did it, I think I got 4n times n plus 1 for a. And you could just, these cancel. This is a 2. The maximum, you know where it occurs. You add up, n minus I, and you get something of order n squared, and it's this. And in this example, we know, because it's a nice enough example so that you could know what the eigenvalue is. And so we get, an honest bound. So we get beta is less than or equal to 1 minus 1 over, what did I actually do? Okay, actually, when I did it, this was a 2. I did my work, so this is 2 n times n plus 1, and here actually beta 1 is equal to some cosine of some sort or other, cosine of pi over 2 n minus 1, which is 1 minus pi squared over 2 n minus 1 squared lower order terms. And so, the bound is fine. And people who have used paths, you can use them in very complicated problems and get some information. So this is the start of path technology. And there are many other problems that we treat in the paper. I want to, there's the clock, good. I want to tell you one other application, so I'm not going to do them. But path technology is quite evolved. You can use randomized paths. You can use weights and Cauchy-Schwarz. You can use local Poincare. And we even have a way of doing, in the paper, we have a way of doing log Sobolev. So, okay, that's a direction. Okay, so end of part 1 of the talk. Okay, Luke is still awake. He doesn't look so awake, but yes.
So can I ask you a slightly different question? So is there computational complexity aspect? So in other words, let's take a graph where the walk would be rapidly mixing, say, a hypercube. And now you put in, say, a small number of sinks. And then you say, well, I want to know, as far as the stationary distribution goes, what's the stationary probability of the left subcube, of the 0 subcube? Could it be that this is hard to approximate?
Sure it could be. There's a rich world, and it's not this talk, but there's a rich world of methods of approximating the quasi-stationary distribution. It's a famous problem with lots of study. Let me give you one example of an algorithm, and then analysis of this algorithm is completely open research problem. People who actually do it, it's mostly in biology that people study the creatures, and if one kind dies out, they stay dead, right? So you want to know how that evolves. And so one algorithm that's used to approximate quasi-stationary distributions is start 1,000 Markov chains at 1,000 different, maybe all starting at the same point, but let them evolve independently. When one of them hits infinity, of course it dies, but then what you do is pick one that's alive and put at random and put 2 points there, and then let them evolve independently. Okay, so that, it's a theorem. That process, that's now a point, some particle process. That particle process converges to the quasi-stationary distribution. If you let it run a long time, the empirical measure of the points that are alive is the quasi-stationary distribution. And there's beautiful math just proving that and getting started, but then to try to say something quantitative. So I'm sure there's a rich world of questions of how difficult is it to approximate quasi-stationarity? I think nobody's thought about it, so thank you. I have one other problem that's different but very related that I want to tell you about, or ask you about, or tell you about, and so I'm going to do that. And I'm eager to hear ideas and suggestions, but I'm also eager to tell you this problem. So I'm going to do it. So let me begin with the actual thing, the actual matrix I want to bound. So what I just said is that you can apply geometric techniques to positive matrices where the rows aren't all don't sum to 1, to substochastic matrices. That's all I just said. Okay. Now I'm going to do something else. Here's a matrix I need to get my hands on. I'm going to call it M. And it's equal to this matrix. It's got a quarter here, okay, and it's n by n. And above and below the diagonal, it's got ones. And it's got ones in the corner, I'm sorry to say. And on the diagonal, it's got something. It's 2 cosine 2 pi j over n, and 0 less than or equal to j less than or equal to n minus 1. So can everybody see that matrix? It's constant above and below the diagonal. It undulates on the diagonal, and it's got these ones on the corner. So cosine is not positive. So this isn't a stochastic, anything like a stochastic matrix. It's negative there. The rows don't have a constant row sum, and I need to bound the biggest and the smallest eigenvalues of that matrix. And I'd be very happy to have ideas. I can do this one. I have many other matrices like this. So what I want to do, I will tell you what this has to do with what I just talked about. I want to give you some motivation for this. So why am I doing this, and where does it come in? I will come back and bound that matrix. Okay, so motivation has to do with the Heisenberg group. So let G be equal to the set of all matrices, 1, 1, 1, 0 here, x, y, z. So 3 by 3 upper triangular matrices with x, y, and z contained in the integers mod n. So that's a group. The size of G is n cubed. You put anything in there. It's called the Heisenberg group. Mod n. And it's of interest with elements in lots of places, but it's also of interest. This is also of interest, as I'll try to explain. So I'm going to write such an element as x, y, z. And if you multiply two matrices, x prime, y prime, z prime, well, that's equal to x plus x prime, y plus y prime, z plus z prime, plus x, y prime. You just multiply the matrices. That's the product in this group. And simple random walk on this group is generated by picking one of these two coordinates at random and making it plus or minus 1. Let's write that down. Let S be my set of generators. It's 1, 0, 0, minus 1, 0, 0, 0, 1, 0, and 0, minus 1, 0. Those generate the group. And if I let Q of G be equal to 1/4 if G is contained in S and 0 otherwise. That's my random walk. So each time, multiply, pick one of the 4 matrices at random, multiply on the left, and that converges certainly to the uniform distribution as long as n is odd, because there's a parity problem otherwise. You could put the identity in if you like. But if n isn't odd, then this converges to, so Q, this Markov chain, Q star K, G converges to 1 over Q. And I want to know how fast this comes. And if you're not, don't get nervous about groups. It's you have a graph. The vertices are these matrices. You connect 2 if they differ by a generator, and then you're studying the random walk on the Cayley graph of that group. And so there are many ways of approaching this problem. One that I always wanted to do and have just done, and this is joint work with Dan Bump, Angela Hicks, Laurent Miklo, and Harold Whittam. So it took a lot of us to do this problem. It's natural to try to study random walks on groups by using Fourier analysis. And let me just say in a sentence what that's about. A representation of G is a mapping rho from G into matrices, GLV, with the property that rho of ST is rho of S, rho of T. So it takes products into products. The Fourier transform of a probability at a representation is the sum of Q of G times rho of G. So it's a matrix. You just add up the matrices, and this thing is the Fourier transform at a certain irreducible representation. As usual, the Fourier transform of a convolution is the Q hat at rho to the kth power. So Fourier transform takes convolution into products. The Fourier transform of the uniform distribution, U hat at rho at an irreducible representation that's not trivial, is 0. And so you study rates of convergence of random walk to their stationary distribution by studying how fast do these matrices converge to 0. And an effective way to do that is this upper bound lemma, the distance of Q star K minus U in total variation squared, it's the same upper bound lemma, is less than or equal to, now here's the sum over rho not trivial of the dimension of rho times the Frobenius norm, the trace norm of Q hat at rho to 2kth power. So this is just the sum of the eigenvalues if they're symmetric to the 2kth power. But I could put the 2k inside. This is an upper bound. So where this sum is over all irreducible representations, which are not trivial. And so you have to get your hands on these things. For this group, it's actually, so if you do this over the integers, just over Z, nobody knows the representations. And maybe you could prove, if you like complexity, that nobody will ever know. Okay? Seems to be a hard problem. For the integers mod n, oops, that's not a good way to do it, but this will be better. It's harder. It's good exercise. For the integers mod n, I can do it. Let me just tell you what it is when n is a prime. It's easier, but it's very similar. Okay, this didn't like being Persi handled. So for our G, let me tell you what the representations are. There and n is prime. It's just easier. I'm happy to tell you offline if you want to know the rest. So there are p squared one-dimensional representations and p minus 1 p-dimensional representations. Let me tell you what they are. So rho sub a b of x, y, z, this is the index of representations, is just e to the 2 pi I over p times ax plus by. Just what you think it would be. And here, for the p-dimensional representations, let v be the set of all functions f from z mod nz into c. So just vectors of length n. And rho sub a is now non-zero mod p of x, y, z, acts on a function f, and its value at j is something, e to the 2 pi I over p times a times, don't tell me, y times j plus z times f of j plus x. So you act on functions by translating by x and doing this, multiplying by that. And you can, easy to check that those are representations. A is anything mod p. A and b can be anything, and those are all irreducible representations. Okay, so that's classical. And now I have to do this. When I do this, for the p-dimensional for the one-dimensional representations, it's just cosine. There's nothing new. You have to do some Fourier analysis. But for the p-dimensional representations, so q hat at rho of a is a p by p matrix is equal to just what I said, 1/4. These are ones, and there's ones here, and here is cosine 2 pi a j over p. And so this matrix has a natural story. If I have time, it has, well, I don't have time, so it has many natural stories. Okay, just to, time is essentially over, but let me just tell you what's the connection between the two parts of the talk. So I now need to bound the eigenvalues of this matrix, and well, so first of all, I can make things positive by adding the identity, right? So I plus m, 1/2 I plus m, is now bigger than or equal to 0. Just that makes things positive, and then I can fix and make something which has rho sum summing to 1 by appending infinity, and then well, let's see. I think it's 1/3 I plus 2/3 m now is substochastic. That is, all the rho sums are less than or equal to 1. And so I just do this. I make 1, here's 0. And now here's my, call this thing L. L is here. And here's this L. And now I just put in here whatever I need to make the rho sums 1. A1. And then I think what these things are AJ is equal to 1/3 plus 2/3 cosine 2 j. The largest eigenvalue of this, of course, is 1 from the absorbing state. And the second largest eigenvalue is the largest eigenvalue of this matrix. And now I can use my geometric arguments, and you can show it's not bad at all. A little bit of cleverness, but well, there's a little work to do, of course. But you can show that this beta, which is the top eigenvalue of this matrix, is 1 minus pi over 2n in general, plus big O 1 over n squared. And I also, let me pay over n. So I can get my hands on the biggest eigenvalue. I can also get my hands on the smallest eigenvalue, and that needs very different arguments. Using that, last line of the talk, using that you can show that if you run this random walk, it takes n squared steps to get random, and that's necessary and sufficient. So time is over. Let me just say what I've done. I've said there are two problems I ran into where I had matrices which were not adjacency matrix of graphs, but not so far away from them. One was quasi-stationarity, where the matrices are positive and substochastic, and the second was this kind of matrix. And in both cases, we could change things around, and we're able to use the geometry of an underlying graph in order to bound spectra. I want to say one more thing, which is this matrix is a famous matrix. It has 100 papers about it. It was one of the reasons the last Fields Medal was given, just for people who care about things like that. It's called Harper's operator. The spectrum of this matrix is called Hofstadter's butterfly, and Arthur Avila got the Fields Medal in part. He did many, many wonderful things, but for solving what's called the 10 Martinis problem, and the 10 Martinis problem is understanding the limiting spectra of these matrices. Without knowing that, we rooted around, did our work, and we know things that the community doesn't know and seem interested. So spectral geometry is still alive and well. It's time to stop. Thank you.